Bismillahirrahmanirrahim. New syllabus SSC 2 Physics Unit number 10 Simple Harmonic Motion and Wave. Spring, mass spring system, ball and bowl and simple pendulum. Today we will discuss about simple pendulum in detail. So, what is simple pendulum? First of all, see in this diagram, we consider a length of string L and a mass of bob M attached with the string and vertically in this diagram. Here making an angle theta, theta and S be the position on the right. See in this diagram. And theta and S is the negative when it goes to left. So this motion is left to right about its mean position. So we can give the example of simple harmonic motion SHM, and SHM example is body is displaced toward the mean position and it is always directed toward the mean position. Here we can see that the weight toward the downward and tension toward the upward. Both are cancelled to each other. So, according to restoring force, only work will be produced. So, in this diagram, we can see that the work will be produced W sine theta. W is equal to mg and sine theta is the angle represented in this diagram. So tangent axis is our W is equal to sine theta. The weight has the tangent component, so W is equal to minus W sine theta, minus sine due to the restoring force. And this angle shows the tension, tension in a string. The tension is directed toward the center of the circle. This is the tangent component. So tangent component T and W cos theta cancel to each other and work is always to downward. So we can write that a pendulum is a mass suspended from a pivot point by a light string of a or a rod. Now we can write that the mass move along a circle arc. The net force is the tangential component of the wave because here we can see that W is equal to minus W sine theta. This minus sign shows that toward the restoring force and toward the mean position. So we can write that the net force is equal to force of tangent and is equal to weight of tangent Wt is equal to minus mg sine theta because W tangent is equal to minus W sine theta, W is equal to mg. So we write that net force of tangent is minus mg sine theta. Now we can know about simple pendulum. In this diagram, we can discuss completely. The equation is simplified for a small angle because we have sine theta is approximately equal to theta. Now this it is called a small angle or approximately angle due to the restoring force. Restoring force in this diagram minus mg sine theta. So you can write that net force minus mg sine theta is approximately equal to minus mg theta. Here we can find the angle theta. So in this diagram we can see that theta is equal to theta is the angle along the base and this is the perpendicular side and L is the hypotenuse. So sin theta is equal to perpendicular over hypotenuse. So theta is equal to S upon L. So we write that minus mg over L into S. Now this is the net force. The force on a pendulum is in a linear restoring force for a small angle. Then pendulum is moving in a simple harmonic motion. Now we can write that the simple pendulum motion is the simple harmonic motion. In this diagram, we see clearly theta is the smallest angle and S is the perpendicular toward the displacement S and L is the length of rod or spring. The restoring force is proportional to S, the displacement from the equilibrium. So net force is always directed toward the mean position. So we can write that this is S is an arc length. The tangent restoring force for a pendulum of the length L displaced by arc S. It is denoted by in this diagram F net force is equal to minus mg over L into S. So this is the same linear restoring force from the spring, but the constant as a mg upon L. So we can write that this value is equal to K. Now we have restoring force and Hooke's law F is directly proportional to S because we know that according to the Hooke's law force is directly proportional to its displacement. So we will discuss about the time period. So we find the time period in simple pendulum. Write this formula. The acceleration and displacement in a simple pendulum is related by its time period t. So by the following equation, we can write that A is equal to minus 4 pi square upon t square x. X is the displacement. And we have A is equal to minus g over L. Now comparing both equations, so we write that minus g over Lx is equal to minus 4 pi square over t square multiplied by x. X cancel out by this x and minus sign cancel out by minus. So we can write and rearrange the equation g over L is equal to 4 pi square upon t. Then taking square root on both sides, this is equal to T is equal to 2 pi L over G square root. Now this is the time period of simple pendulum. We can repeat again time period of the simple pendulum and the frequency. Here we can see that lower frequency shows the long pendulum and weak gravity, but high frequency shows the short pendulum and strong frequency. So strong gravity will be increase the restoring force. This is increase the frequency. Here we can see that G depend upon the value of G and also depend the L. Increase the length of simple pendulum, then decrease the frequency because F is equal to 1 upon 2 pi into G over L. And similarly, if L is increases, time period is increases, but frequency is decreases. Now we will discuss about the frequency can be obtained from this equation of given by F is equal to 1 upon 2 pi G over L. Here substitute the value mg over L in the place of K. Then we have F is equal to 1 upon 2 pi G over L and T is equal to 2 pi L over G, time period of the simple pendulum and frequency of the simple pendulum. So frequency and period of simple pendulum L with the free fall acceleration G. Now we detail of the pendulum motion, we can see that in this diagram, as far as the mass of spring, the frequency does not depend upon the altitude. Because note that the frequency and hence the period is independent of mass. So it does not depend upon the mass, it depends upon only the gravity and the length of pendulum. So we can write that simple pendulum is the pendulum consists of mass at the end of the high light or high weight or light weight, both are same, not depend upon the mass. so mass is negligible. So we can write that the simple pendulum in this diagram we can see that here L is the length of the pendulum and F is the force or tension toward the length and mg cos theta is the weight toward the vertical component. So cancel out each other and it will be 0. But due to the restoring force mg sin theta toward the mean position. Here we can write that in order to obtain the simple harmonic motion, the restoring force must be perpendicular to the negative displacement. Here we can write that restoring force F is equal to minus mg sin theta, which is the proportional to sin theta and not to be a theta itself. So we write the table and here we can see that if the angle is small, so we can write that sin theta is approximately equal to theta. So the pendulum is timely in this bow diagram. We can explain this. Here in A diagram we can show first L cos theta and L minus L cos theta and L is the length. So in a circular path of the pendulum and this is the shortest point between the equilibrium position and the mass of bow and this is called the displacement and force is directly proportional to its displacement. So we can write that tension T along the string and weight toward the vertical component of this axis and making angle theta between the weight and W cos theta. So we write that here other force, this is a restoring force toward the mean position. So we write that the tension and mass can be denoted and mass cannot be depend upon the length or frequency of simple pendulum. So F tangent and mg tension T toward the upward and we write that F tangent is equal to minus mg sin theta. Sin theta is approximately equal to theta, so Ft is equal to minus mg theta. Similarly, theta is equal to S over L. So comparing the spring constant and pendulum now force is equal to F is equal to minus kx in a spring system. But in other pendulum system, F is equal to minus mg S over L. This is for the pendulum. Now, force depend upon the position, reverse direction at a same position. Now, periodic motion, we can see in both cases x is equal to x naught cos omega t and in other case s is equal to s naught sin omega t. So we have discussed about that also in a pendulum theta is equal to theta naught sin omega t. Angular frequency in both cases we can see that omega is equal to k over m whole square root and in other case omega is equal to g over l square root. Now we have the simple pendulum is the best example of simple harmonic motion. Therefore, for a small angle, the force approximately proportional to the angular displacement. The period and the frequency are written as T is equal to 2 pi m over k and always equal to 2 pi m. K values is putting here mg over L. Then it converted into the simple pendulum T is equal to 2 pi L over G, m cancel out by m and theta be the smallest angle. Similarly, frequency can be reciprocal of this. So, frequency is equal to 1 upon 2 pi G over L square root. Then we write that frequency and period. Now here we can see that frequency and period. One node to other node or one antinode to other antinode, this completes the one time period. So in this heartbeat, voltage occur in chest and time period along the x-axis. We can see this diagram, this point to this point, one revolution will be completed and time period t. So we can write that the oscillation of the time period complete for one cycle. This is called the period and it is denoted by t of the oscillation time period. F is equal to 1 upon t. Frequency is the reciprocal of time period. So time period t is equal to 1 upon f. Now the number of cycles per second is called the frequency and it is denoted by f of the oscillation. Now the unit of frequency or hertz or per second and the time as the unit is seconds. So we can write that both are reciprocal to each other. Best of luck. Thank you. Next lesson with next video. Best of luck.